Welcome everyone, and thanks for joining us today to learn more about Miovision's automated traffic signal performance measures. I'm Shannon Hebert, the ITS Marketing Manager here at Miovision. Before we get started, I wanted to go over a few housekeeping items. We do have all of your lines on mute so we can reduce the background noise, but you can still communicate with us. Using the question box on the screen, you can enter in your question, and my colleague Brent is here, and he'll be monitoring the questions as they come through. We plan to leave about 15 minutes or so at the end of the hour to get to all of your questions. We'll also be taking a few poll questions during the webinar. This is so we can get a better understanding of how familiar you are with automated traffic signal performance measures and where your interest lies. Finally, we're going to be recording the webinar and sharing it with you afterwards so you have a reference point or can share it with your colleagues. So with that, let's get started. This past spring, we debuted Clear Signals, our practical guide to using Miovision's automated traffic signal performance measures, or ATSPMs, to keep your intersections healthy. We had such an overwhelming response to the ebook and requests to learn more that we're excited to be back with you today to share some new examples of how to implement and use ATSPMs. With me today is Sajjad Shavari, who is our in-house traffic engineering specialist. Sajjad works closely with our solution experts and customers to unlock the power of ATSPMs. And in doing so, he's analyzed the health of hundreds of intersections across North America, and he's taken this knowledge and created our ebook. For those of you that are new to automated traffic signal performance measures, there are a tool set within Miovision's TrafficLink that allows you to leverage data collected at the intersection so that you can ensure that your intersections are running properly. Whether your priority is to maximize arrivals on green or minimize pedestrian delay, ATSPMs can help you measure the performance of your intersections with this high resolution data and compare that performance against the objectives that you've set. Sajjad is going to walk us through a few examples, but before he does, it'd be a good idea to get an understanding of how familiar this group is with ATSPMs. So I'm going to go ahead and put up our first poll question, and it simply is, how familiar are you with automated traffic signal performance measures? I'll give you a few seconds to answer this, and then we'll be back. As we expected, it looks like the majority of you are here to learn more or just starting to explore. So it's a perfect time to pass the mic over to Sajjad so he can show you some examples of ATSPMs in action. Sajjad?
Okay, thank you, Shannon. Hello, everyone. This is Sajjad speaking. Really appreciate you taking the time today to attend this webinar. Hopefully it's going to be a good one. Seems like we have a mix of people who already attended our previous ATSPM webinar and people who are new. So the good news is that we have content for everyone. We're going to do a brief introduction to the ATSPM data first, and then we're going to move into some brand new examples of how the ATSPM data help evaluate the performance of signalized intersections and corridors and improve their performance in real-world examples. So just to start off with, so ATSPM is an acronym for Automated Traffic Signal Performance Measures. These were ideas that came out of the transportation group of Purdue University in collaboration with a number of public agencies in the United States. And the whole idea is that there's all sorts of sensors and connectivity that's available in the field, and they're producing a lot of data. So the Internet of Things, and the new sensors that are becoming more and more frequently available in the field, they're creating a lot of data. And the whole idea was, okay, is it possible to capture that information and bring it in and develop performance measures that can actually help get a better understanding of the performance of signalized intersections and corridors to be able to maximize what we can get out of the current road network. So just to kind of as a basis of ATSPM data, there's really three main data sources. The first data source is coming from the traffic controller. So the traffic controller, it's logging all sorts of information. One of the basic pieces of information that it logs is the phase interval. So the interval duration of the green, amber, red, all that information is coming from the controller. Some controllers also have the capability to actually log what they're doing. So for example, the phase termination reason. So this was a phase that it gapped out, or this was a phase that maxed out. So even getting that information. So I find even that piece of information to be able to understand what the controller is actually doing in the field is super valuable in understanding whether the timing plans that are on the paper have been actually implemented properly in the field, and whether the controller is actually able to actually keep those timing plans as they were designed. I've seen a lot of cases where that hasn't been the case. So just being able to verify whether that's the case or not is extremely valuable. Another piece of information that's available at actuated intersections, for example, is detection. So detection, that the main purpose of the detection is for actuation purposes, but it's also possible to take that info, combine it with other sources of information that's coming from the controller, for example, and being able to generate new performance measures. So for example, the stop bar detector occupancy during the green time and during the red can help us evaluate and understand the level of saturation of a movement, for example. We'll look into some of those examples later on. And a third piece of information that's also available, for example, through the Miovision system, is the MAC address probe information. So through an antenna, capture MAC addresses, we match them from one intersection to another, run it through a filtering algorithm to get rid of the outliers, and then we have travel time information as well too. So that travel time information, it's possible to take that, convert it into speed, generate all sorts of different indexes and congestion scans around it that we'll see as we go through these this presentation today. So what makes it possible? So you might think, okay, where is all this data coming from? How are you capturing it? I don't want to go into the details, but in this context, it is the Miovision Smart Link that goes, it's box, it goes into the cabinet, connects to the controller. It also provides connectivity if there is no connectivity at the cabinet. If there's already some kind of communication available, it will connect to that. And then accompanied with that is the TrafficLink portal. So TrafficLink portal is a web-based software that really brings all of that data to life. So aggregates it, provides all sorts of different aggregation and visualization features to really be able to take advantage of that data that's being produced. So just to step back a little bit before we go into the examples, we've talked about the data, but data on its own, if it's not going to be used, if it's not going to have an impact, it's useless. So let's step back a little bit and see, like, why do we need this information? Why is this information and this data valuable? And this really goes back to objectives. So especially for signal timing objectives, there could be different objectives based on the time of day, based on the intersection, based on the location. There could be different objectives that are suitable for an intersection or a corridor. So for example, at a specific time of the day, a corridor's objective may be to just maximize the throughput throughout it. You want to maximize the number of vehicles that you can get throughout the corridor. And other times throughout the day, it might be provide more equality between the movements. So depending on where you are, where the location, the objectives could be different, but the whole point of the data is to be able to inform these objectives and to be able to, in a very simple way, being able to tell you how close you are to these objectives. And also, it can also help inform the objective as well too. So not only to support the objective, but sometimes it could be different. So let's say there was an example where we had a coordinated timing plan throughout the entire day, but we realized through the data that actually there were times throughout the day the major was super undersaturated, and by allowing the intersections to operate in free mode during those hours, it would reduce the delay a lot for pedestrians and the minor streets. So the data was informing an objective as well too. And the data could be used for addressing complaints as well too. That's a basic functionality of it as well too. So if there's some kind of complaint coming in, it's possible to go back to the data, go to the intersection behind the computer, and then analyze what happened exactly at that time, what's the problem, is there something that can be done about it. So it really depends on the objectives and what the agency deems suitable for their intersections. From our perspective, we talk about healthy signalized intersections and corridor. And by healthy, I mean intersections that are achieving objectives depending on what the objective is. So for one location or from one area, healthy could have a different definition to another location. But what's important for all the intersections is that they need to be able to perform perfectly well at 3 levels. The 3 levels are maintenance, operations, and optimization. By maintenance, we mean the detector needs to work, right? So communications, the signal, the detection, it needs to work properly. So if you have a detector that's broken and it's failing on high, and every single cycle it's being called and it's reaching its maximum because it's failed high, that's a maintenance problem. And the maintenance problem can impact optimization. So regardless of how good your timing plan is, if at the maintenance level, you have problems at the maintenance level, you're not going to be reaching the full potential of that optimized plan. At the operations level, it's kind of midway, so it's not really a maintenance problem, it's not an optimization problem, it's somewhere in between. And these are cases where the prerequisite to an optimized plan isn't there. So just to give you an example, a corridor that is coordinated needs to operate on a similar cycle length throughout the time of day plan. So if there are no cross corridors, just one corridor, major direction, all the intersections need to operate on the same cycle length during the coordinated plan, if the objective there is to coordinate. But when we go to the data and see that like 2 of the intersections, for whatever reason, are operating on a different cycle length, that's the operations problem. So we can't even talk about optimization. We can't even evaluate the performance of the actual timing plans before we actually go and fix those cycle lengths to be the same. Now you let it run. Now you go back to the data to see how it's performing, and now we can talk about the next layer, which is optimization. And at the optimization layer, we're talking about the splits, the cycles, the offsets, the common variables that everyone talks about. So just to give you an example, on the bottom right corner, we have, let's say there's a major signal retiming, and the y-axis there is the health rating of that intersection or a corridor. What will happen is that after time, so it's not just about a one-time thing to make sure that the signal is, or the corridor is retimed and working healthy, is to be able to keep that healthy. So as time passes by, there could be a detector failure. That impacts the health. There could be a clock drift. That impacts the health. Then there, as time passes by, driver behavior is changing, or traffic routes are changing, and there's a split allocation problem. So all of these contribute to, again, the deterioration in the health of the intersection of the intersection and the corridor. So here we'll go through some brand new examples around how the data can be used to really analyze and improve the performance of the intersections. So this intersection, this is an installation that we had. It's within a residential neighborhood. There's a major highway that crosses through the intersection. There's residential neighborhoods both on the east and west side of this intersection. There's a middle school with school traffic, the seasonal traffic from the schools as well too. And as you could imagine, there's definitely going to be competing objectives here. There's going to be a lot of traffic, turning movement traffic. There's a lot of traffic along the major highway. And our equipment was installed at this intersection to be able to get a a better understanding of the performance of this intersection. Because there was a smart sense device here, we were actually able to get 24/7 turning movement count data. So there's on average there seem to be around 25,000 vehicles, 3% trucks. There's a number of pedestrians there throughout the day. AM peak and PM peak. Our AM peak seems to experience around 2,000 vehicles, and then the PM peak is 2,200. You can actually see the spike in the volume here during the AM peak. This is very much probably related to the school traffic at that time. Seems to climb from then, and then there's another spike as well here to around 3 p.m. It seems to be related to the school traffic, then goes down again a little bit until the PM peak kind of kicks in. So this kind of gives you a good view of the performance in the intersection from a vehicle volume perspective. But from an ATSPM perspective, we can get a much more, so that's volume, that's just demand. That's what the industry is usually used to measuring. But there's more to measure here as well too, and to be able to really get a grasp of the performance and being able to identify problems. So the method that I use, which it's also available in the ebook, we actually have that checklist. I go through a checklist to be able to make sure that all different components are working properly. There's suitable phase terminations. There's effective usage of green time on the miners. Miners are getting their green time. They're using it. They're terminating properly. Are there movements that are experiencing oversaturation or split failure? So that the data can help kind of put this, kind of go through this checklist and check mark and red flag issues that can be potentially looked into and evaluated and hopefully improved. So this is a case like that. So we kind of went from the left checklist to the right checklist. There were two issues here at this intersection that we were able to identify through the ATSPM data and being able to address it. So what were the issues? Before I explain the issue, because I'm going to be using this graph, this ATSPM graph a lot, I need to explain it for a quick sec. So the graph that you're seeing on the screen is we call it a split trend graph. It's basically a performance graph. So each movement at an intersection that has a stop bar detector would have a graph like this. And what it's doing is that it's telling us over a 24-hour duration, what is the performance of this movement? And it does that through the stop bar occupancy. So just to give you an example, in number one, there's a queue of vehicles waiting, they get their green light, they're passing through, and by the end of their green light, so the start of the red light, there's still 3 vehicles remaining, so they're still occupying the zone. That's a good sign that this movement is near saturated or oversaturated. That would be the red in this case, which we call a split failure. There's other categories in here as well too. So let's say there were less number of vehicles based on the green time that was allocated here. So there was actually spare capacity. So let's say the usage of the stop bar detector was less than 60%, it's 40% or 30% usage. That would be the blue bars. So the spare capacity, it means that there's extra capacity available at that for that movement during that time. There's the OK one. So OK is pretty much in the area where there was a queue of vehicles, they got their green light, they passed through, and by the end of the green light, there was no one remaining on the stop bar. So that's kind of in the OK zone. So depending on kind of where we are on that green occupancy ratio, red occupancy ratio, we're able to classify each cycle into one of these categories. So just to give you an example, around 4 p.m., it seems like that bar, one of those bars is a representative of 15 minutes. It seems to be around maybe 60% of the cycles are experiencing split failures on this movement, and maybe 40% are experiencing kind of in the OK zone, or they're passing their queue properly. So being able to see that, it's clear that for this movement, for example, around 4 p.m., there's a spike in the number of split failures that happens, and it ends around 7 p.m. So with that introduction, let's go back to that example that we were talking about. So the graph that you can see on the top is the split trend graph that we talked about. One of the things that it's important is to be able to evaluate this kind of on all the competing movements at the intersection. And from an operational perspective, a minor movement, let's say a left turn movement, if it's getting its green time, it should be serviced, and by the end of the queue, when the queue is served, it should terminate properly. So that's very important for minor movements to behave this way. This is kind of an objective type of the objective that needs to be reached. So in a case like this, the intersection was operating in free mode. It was suitable operation for this intersection, and the northbound left turn movement was a only protected lagging left. So it was lagging left that was only protected. So the southbound through would be serviced, and then when it would gap out, the northbound left turn movement would be serviced. So something that, again, in the checklist evaluation that I was kind of looking into, we realized that northbound left turn movement is a minor movement. The objective for that is to terminate properly, but we're seeing a lot of blue. This means there's a lot of spare capacity on a minor movement that is not supposed to have spare capacity. It's supposed to use its green time effectively. And then the good thing here is that we actually had a SmartSense device or a camera to be able to actually verify whether that's happening or not, how bad it is. So the left turn movement, this is the case like at minute 10:15, northbound left turn is serviced, and until 10:36, it just remains in green. You can see the southbound through movement being delayed for no reason. So this is definitely a problem here that that needed to be addressed. So in order to address this problem, the agency came up with a very innovative way of, okay, let's enable the southbound through movement to be reserviced. So when the northbound left turn is being is serviced, if it's gapping out, allow it to gap out and reservice the southbound through movement within the same cycle. So within the same cycle, the southbound through, if this case happens, can be serviced 2 times. So this was implemented, and then the good thing about ATSPM data is that you can immediately go back to the data and see, okay, what was the impact of that? And the impact of that from all sorts of different perspectives. So one of the bottom left graph that you can see is the same split trend graph that we talked about. We saw a lot of blue at that time. Right now it's a lot of more green, so it means that there's much more efficient usage of that northbound left turn movement now. From a green allocation perspective, that's another ATSPM. So green allocation is the percentage of the green time that each movement is receiving throughout the day. So the bottom line here is the before duration, and the top line is the after duration. So in the after duration, the southbound through movement is consistently receiving a larger proportion of green time. And that proportion is around, as a trend, seems to be around 11%. And then if you kind of do the multiplication over 6 hour duration, that means over 40 minutes of extra green time that was unlocked for the southbound through movement through this very critical fix here. So I'm just going to run a video here just to show you how this reservice works. So the vehicle that's standing on the northbound left turn lane here is waiting for a green light. As I said, it's only a protected northbound left turn movement. It gets its green light, passes through, and this is after the fix. So before the fix went into place, until there was demand on the northbound through movement, it would continue to service the northbound left turn movement. But now you can see that it reserviced the southbound through. So all these vehicles needed to wait an extra cycle in order to pass through. So really had a massive impact on the performance of the southbound through movement as well too. So that was one of the issues. So that was the operational issues. If you remember, we had kind of two red flags there that were kind of checked in the checklist. That one of them was the operational issue that we saw in the previous one. So that's kind of the first step. So the first step is to make sure from an operations perspective, everything is set up and all the prerequisites are there for an optimal plan to work properly. Another component in there was more of an optimization problem or split allocation issues. So if you look at the top right graph there, you can see, again, we're looking at the split trend graph. It's a very useful graph because it gives you one view of the performance of that movement. You can also run trends on it. So each bar represents a 15-minute duration. So if you run a 2-week trend on the data, it will actually go and capture 2 weeks of data and give you an average value of that. So this type of visualization of the split failures or the split trends really helps with that aggregation feature as well too. So as you could see, throughout the day, the westbound left turn movement as a trend was experiencing split failures both during morning and the afternoon peak. Afternoon peak, it seems to be around the school hours, morning peak as well too. Morning seems to be kind of worse than the afternoon, but the thing is that this is a trend. This is a trend that's happening every single day. And again, this goes back to objectives. So the agency deems suitable that at this time, we want to make sure that there's equal opportunity for competing movements at the intersection. So when we look at the competing movements, which are the southbound through and northbound through movements, as you can see on the bottom left corner here, you can clearly see that the northbound and southbound movements throughout the day are experiencing less saturation. For the contrast here is really obvious because the northbound, southbound, you're seeing more blue or spare capacity, you're seeing more green in the OK zone, but once you're looking at the westbound left turn movement, you're seeing like a lot of red or split failures that are happening. So the imbalance in performance is really obvious there. So this really goes back to engineering judgment as well too. So at this time, it seems like the objective here is to be able to create a more equal opportunity for the westbound left turn vehicles to be able to pass through. This is a screenshot of that occurring. So the video really helps to validate that this problem is existing, how bad it is. You can clearly see that the queue of vehicles that are waiting just at the start of the red that weren't able to pass through. So a fix that the agency put in during this time was, okay, is operating in free mode. What we'll do is that we'll increase the green time, the maximum green time on the westbound left turn movement by 10 seconds. So let's go from 40-second maximum to a 50-second maximum. This can be seen on the bottom left graphs. The bottom left graphs is called a phase interval graph. It's actually showing us how much red, green, and yellow is being allocated to a movement. In the TrafficLink system, you can actually click on the red, for example, and we'll get rid of the red portion of it to be able to exactly see what's happening. So in the before duration, you can clearly see that during the AM peak and PM peak, there are quite a few cycles that were hitting that maximum green time of 40 seconds. There was an increase of 10 seconds for this movement. As you could see, again, during the AM peak and in a few cycles in the PM peak, they're also hitting that kind of that maximum. So it's very obvious that they actually needed that extra green time. The westbound through or the westbound left turn movement really needed that extra green time. So from a performance perspective, that was from a signal timing perspective, but from a performance perspective, we can go back to the same split trend graph that we were talking about. So in the before duration, we're seeing a lot of red or split failures that were happening. The intent was to address this, that the 10-second increase in the maximum green time was the way to be able to address that. And we can go back to the data. So after 2 weeks, run a trend on the data and be able to see, okay, have we been able to address this problem or not? So as you can see, it's completely gotten rid of that extra those split failures that were happening, and the performance is much better. We can also look at the performance. I haven't brought the graphs here, but the northbound southbound movement barely saw a change in their performance. So they were operating well, and after the change, it was pretty much the same thing. So addressing this problem without really significantly impacting the northbound southbound movement. With the previous fix, the southbound through movement already had gotten an extra amount of green time. This was, so as you can see here, this is kind of a screenshot of that. So you can see the left turn movement, the queues are clearing properly, there's a school bus here, and then we're not seeing the same issues that we were seeing in the before the change happened. So really had a massive impact, and the video really helps get a better image of how that's impacting and what that means. So this was a case where it kind of went through the checklist, an operations issue, an optimization issue at an intersection. I'm going to go through an example for a corridor here and how the ATSPM data helped evaluate the performance of the corridor, being able to get a better understanding of how it's performing, and then the fixes that were put into place using the data in order to improve the performance, again, based on the objectives. So this is a corridor. 4 intersections. Our equipment were installed on 4 intersections along the corridor. One of the intersections on the top also had a smart sense device, so that would be the camera that enables the turning movement count data, the 24/7 turning movement count data. But the other intersections didn't have the turning movement count data. We only had the ATSPM data available. This is a corridor that connected a downtown area to the northern suburbs, so lots of directional traffic during the AM and PM peak. During the AM peak, it was more going southbound, and during the PM peak, it was coming northbound. So it seems to be lots of complaints around long queues and delays along the corridor. So our equipment was installed to get a better view and better visibility into what's happening along this corridor and whether it can be addressed or not. So one of the graphs that can easily help, especially from a corridor perspective, being able to quantify what's happening, what the performance of the corridor is throughout the day, is the congestion scan. So this is a travel time graph. So it's coming from the travel time data. This is another way to visualize travel time information. So for people who aren't familiar with the congestion scan, basically what we're doing is that for each 15-minute duration, we are generating a travel time index. And a travel time index is the median or average travel time over the free flow travel time. And the reason that this index is really good is that because it gets rid of that distance factor in travel time. So different sections of the corridor might have different distances, and because of different distances, they might have different travel times. But in order to be able to compare the travel time of different sections, we can use the travel time index. So travel time index, we're visualizing that for both sides of the corridor in this graph. So the right side is the northbound, the left side is the southbound. And as you can see throughout the day, it's color coded, so it's very obvious that the northbound direction during the PM peak is experiencing congestion, is experiencing a significant amount of congestion. So this is a 2-week trend. We're seeing a significant spike in travel time, seems to be around maybe 3 to 6 p.m. And travel times are up to maybe 12 to 15 minutes. For a length of the corridor, that should be around 3-4 minutes. Now, that was from a performance perspective, but what can be done about it? That's the part where ATSPM data really comes handy, is that what can we do about it here? So we can go into the controller's operation. So the controller operation, as you can see, the graph that you can see on the screen, again, this is a phase interval graph. This is a graph that's showing us the intervals, red, green, and we can actually see the cycle lengths on the northbound through movement here. So we can actually see that during the AM peak and PM peak, the cycle lengths aren't short. It is actually quite high because they're operating in free mode, and the cycle lengths are, in a lot of cases, are reaching pretty high values throughout the corridor because there is demand for it. Something that can be inferred from this is the natural cycle length. Because it's operating in free mode, we can actually see the natural cycle length that's happening during the AM and PM peak. And that could help inform potentially a coordinated plan. So what is the natural cycle length? I can probably use a percentile to be able to find what the optimal is and to be able to implement that. The data also shows, again, this is a phase interval graph. It's showing us the cycles that are happening. Sometimes cycles are really, really short. So the major is being interrupted during a very congested time to service 1 or 2 vehicles on the minor. So very short interruptions. We're seeing very short interruptions on the major movement during a very critical hour where it shouldn't be happening. Again, maybe from an objective perspective, midday, it makes sense to create more an equal opportunity for the major and minor movements. But during a critical hour like this, the objective is to maximize the throughput throughout the corridor. This could also be creating a downstream issue. So once you have an intersection downstream that is being interrupted, it will create a demand starvation for the downstream intersection, and the downstream intersection might be wasting their green time. And overall, doesn't seem to be a good situation. From a coordination perspective, we have a time-space diagram. So we have a time-space diagram that actually show you the green bands that are happening northbound and southbound. So in a case like this, the intersections were not coordinated. They were operating in free mode. You can see that there's barely any coordination happening or green bands that are happening. Very clear that there are cases where downstream intersections are in green while the upstream intersection is in red. And that's just wasting a lot of green time, and that's just not optimal for this hour. So what do we know to this point? So there's PM peak is experiencing significant delays. There seems to be a lot of randomness in operation during that hour. The data is also indicating that during the most of the hours throughout the day, except for that PM peak, the mode of operation is actually working quite well. So we didn't see like a significant spike in travel times during that time. So the timing plan makes sense for the rest of the day, probably doesn't make sense for the PM peak. So the data could help coordinate. So the city deems suitable that at this time, based on the indication that data is showing, it seems like coordination could be a good idea. So how could the data inform a coordinated plan here? So we didn't really need to collect volume data. That's one way to do it, is to collect volume data, all the intersections, kind of model it and then optimize it. But another way is to use the current data. So there's the variables that we need here is, first of all, the cycle length. So the natural cycle length that were happening, we could use a 90th percentile here to see what the natural cycle lengths are during this hour. What is the intersection telling us what it needs during that hour? And we can identify those in 130, 120, 120, one is 170. And then we also have the splits as well too. So the split allocation is also there. So the proportion of the split time that's being allocated to the minor movements is also available there. So we can get that from the ATSPM data. So we have the split proportions, we have the cycle length, and based on this information, based on the 90th percentile, the agency decided to go with the cycle length of 140 seconds to implement. The good thing about ATSPM data is that you can implement and then you can go back to the data to be able to see how well it's performing. So the remaining thing is the offsets. You can use a software like Synchro. So you have the cycle length, you can implement the cycle length in Synchro. You have the splits, you can allocate the splits. The volume data at one of the intersections can help with the directionality. So you can actually use that to inform the directionality along the corridor during the PM peak. We have the duration, and now you can use a software like Synchro to be able to optimize the offsets here. So that happened, generated new timing plans and implemented the new timing plans. You can see the new time-space diagram, much better coordination happening during the PM peak. From around 3 p.m. to 6 p.m., a constant cycle length of 140 seconds was considered. You can actually see that constant cycle length happening nicely there at one of the intersections. And definitely the optimism, because there was a significantly higher number of volume of vehicles on the northbound through movement, the offsets were in favor of the northbound through movement. So you can actually see kind of a before after of what the time space diagram looked like before and what it looks like now. So in order to evaluate the impacts, that's the best thing that the ATSPM data could help with. So from a traffic volume perspective, we need to make sure that we're comparing apples to apples. Actually, in the after duration, we actually saw a 2.8% increase in the number of volume of traffic volume that was happening. So not only it went down, it actually went up after the change. From a travel time perspective, the same graph that helped us identify the problem can now help us evaluate the impact. So the before duration, we were looking at a congestion scan. That's the left graph that you can see, congestion scan. And at the PM peak, you're seeing this a lot of red spikes in travel time, or the travel time index. And in the after duration, 1 week after the change, with actually a higher amount of volume, we're seeing a significant reduction in the amount of travel time that's happening here. So travel times are going from a travel time index of 4 or 5 to travel time index of 2. So going from like 12 to 15 minutes to now 3 to 4 minutes to be in this time throughout the day. So much more consistency throughout the day for sure. Again, travel time, there's different ways in the TrafficLink portal to be able to see travel time. One of them, it was the congestion scan. Another way is to just generate a travel time graph from one point to another. It's called the point-to-point travel time. You can see the spike, the median spike in travel time during the before period, and you can see that reduction in travel time in the lower trend graph. So the difference here is fairly obvious. From a percentage perspective, we actually have nifty tools in our product that you can click on it and you can specify a specific hour and it will compare the travel times for you. So you can see during 4 to 6, there seems to be around a 32% reduction of travel time on average. This was for the main corridor. The good thing about ATSPM data, it's also available on the miners. You can evaluate the performance from all sorts of different perspectives. We're just not looking at one perspective. We're looking at other movements as well too. So what we use here is called a report card. So in the TrafficLink system, there's a report card. You can select the before duration. You can select the after. You can select an after duration. It will compare those two for you. So from, let's say from a split failure perspective, you can see that 3 out of the 4 intersections experienced a significant reduction in the number of split failures that are happening on all the movements. So it's benefiting everyone. At one of the intersections, there's an increase in split failures, but that's understandable because one of the intersections, if you remember, was operating on 170-second natural cycle length, but we needed to bring that down to 140 to be able to coordinate. There's an increase there, but that's understandable. There's video there. I actually checked the video. There are split failures, but the split failures aren't massive queues that are remaining. It's 1 or 2 vehicles. So with a simple split reallocation, that could probably be addressed further. The second performance measure that we have is a simple delay on the minor movements to help us inform how much delay the minor movements are experiencing. As you can see here, 3 out of the 4 have either reduced their simple delay or remain pretty much the same. The reason that they remain pretty much the same was that the cycle lengths were already high. The problem was that they weren't just coordinated. That was the thing. One of the intersections, of course, it was favored for the minor movements during the PM peak, and with the coordinated plan, there's an increase in the simple delay there, just to ensure that there's a nice queue before it's being serviced, and it's for the kind of the greater good for the entire corridor. So it makes sense for this to happen, and there's always a level of judgment that needs to go on top of this as well too. The numbers, all the data is there in order to be able to convert that into monetary values or monetary or emission savings. So we have the travel time savings, we have volume that's being impacted. There are formulas available to be able to convert that into how many tons of emission savings that converts to, or how much fuel savings that converts to, or delay savings in terms of people delay. So for this, if we assume that for this case, if we assume that the savings hold for like 300 days per year, that's around $500,000 savings over a 3-year period where it's usually retimings happen. That's around $1.5 million in savings. So it's also possible to not only see the impacts from a travel time perspective and the user experience perspective, but from a economic value as well too. So that kind of concludes my my presentation here. We're going to go through a quick poll question here. First of all, thank you very much for listening. We're going to have Q&A after this, but before that, if you could answer the poll question of, I see the value of traffic performance data for what? Is it for funding purposes? Do you see it for evaluation before after studies? Or do you see it for like signal timing adjustments? We'll wait a few moments to get the results in. Okay, so it seems like there's 37% said that it's good for funding purposes, now 79% for evaluation before after studies, and 90% signal timing adjustment. So this seems to be quite a few people that think that the data could be used and could be helpful for signal timing adjustment. Of course, depending on the type of attendees, funding may or may not be of interest, but it's interesting to be able to see that as well too. So yeah, so here I'll hand it off to Shannon to finish the presentation, and we'll go to questions and answers. Thank you.
Awesome. Thank you so much, Sajad, for sharing your insights and being with us today, and of course for writing clear signals. When we started out on this project, it was exciting to see the many different use cases we had for ATSPMs and the impact that they've had on our customers. So Sajad shared a few new examples that we've collected over the past few months with you today, but our ebook is filled with even more examples and provides greater detail at each level. The book is very well structured with dedicated chapters to guide readers through the 3 levels he talked about today: maintenance, operations, and optimization. As we mentioned, it's very visual with about 80 figures to ensure readers understand what we're referring to in each of the 20 examples, showcasing Miovision's ATSPMs in action. So if you haven't had a chance yet to download Clear Signals, you can do so now by a couple of ways. You can go to atspms.com and download it there, or you can click the control panel on your screen, and then within the handout pane, you'll see the Clear Signals file. Click on that file and your download will begin. Just so all of you are aware as well, we'll follow up today's webinar with an email out to all of you by me, which will have a copy of this recording and also the link to download the ebook so you can share it with your colleagues. Before we get into the Q&A section, and feel free right now to enter any questions you may have in the question section on your screen. I thought it might be important to point out that ATSPMs are part of our Miovision TrafficLink platform. And they're really just one piece of the puzzle that we offer within TrafficLink. Whether you're looking to improve communications between your signals, gain remote access, use multimodal detection, or have a permanent source of traffic counts, TrafficLink gives you the option to implement these different levels of functionality at your own pace when you're ready. And another benefit is that TrafficLink integrates with your existing systems, so you're not ripping and replacing to get smart functionality. So I think we've saved about 12 or so minutes for questions, and we've gotten a few of them that have come in today. So I'll go ahead and share them and have Sajad answer them for us. I think the first one we got here, Sajad, is where do we access or create the time-space diagram in TrafficLink?
Okay, that's a good question. So in the TrafficLink portal, if you click on the analysis tab, in the analysis tab, there is a corridor section up on the left. If you click at that corridor, you can generate a graph and you can select the time-space diagram. That will, by selecting the corridor, so you can set up multiple corridors, and you can access it there. If you have any issues, our customer success team is always here to be able to help you, so feel free to contact for sure. So there seems to be questions around what is TrafficLink? So TrafficLink is the name of the software. So SmartLink device is the hardware that enables collecting the data, and TrafficLink is the web-based software that comes with the hardware in order to be able to access all of this performance measures that we talked about. It's asked how many sensors are in it. So the sensors we are hardware agnostic, so we have our own sensors as well. So if an intersection needs new sensor information, we have a smart sense device that can enable that. Uses AI technology to be able to detect vehicles in different modes of traffic and be able to generate the performance measures. And if there's already detection available at the intersection, we just integrate into that, so that's not a problem. And then another question is, what granularity does the ATSPM data have? Does it present a challenge to store it because of its volume? What kind of database do you use for that? So right now, the data resolution at the moment is 10 times per second for all of the data. We use a cloud-based approach, and that's why we don't need to worry about, and our customers don't need to worry about databases and being able to manage that through IT and that. The data is going to be available indefinitely. So it's cloud-based, it's stored there, and from the time of installation to indefinitely, that data will be available and is stored to be accessed immediately. So no worries about from a database management perspective. How are PEDs detected and served? How does it impact vehicular traffic? So PEDs detected, if you're talking about the examples that we went through, they already had pedestrian buttons there. So in terms of the pedestrian operation, that was something that just remained as it was. Definitely, if there are pedestrian calls, that will increase the amount of green time that's needed to be allocated to a minor movement, which is fine. You can see that data, and you can actually observe that how that's impacting traffic. The interesting thing about ATSPM data is actually you can see how many times throughout the day the PEDs are actually being activated, and sometimes it makes sense to use a different. You don't necessarily need to use the maximum time in order to find the offset, the right offset. If the PED calls are happening like 10% of the day, why use that in order to find the offsets? Maybe you can use the 90% one in order to be able to find the right offsets. If you only have advanced detection, what are the best performance measures? It's a great question. So advanced detection, if you have advanced detection, the performance measures related to advanced detection would be available, and that would be performance measures like arrivals on red and green. So so we associate the arrival of a vehicle on that advanced detector with the signal status, and that's more of a progression metric. If that's the only detection that's available, volume, arrivals on red and green, and the Purdue coordination diagram would be the ones that would be available. The split trend graphs that are related to the individual movement performance would not be available. Do you recommend to solely use ATSPM for vehicle counts for retiming purposes? I think a combination of vehicle counts and ATSPMs should be used, because if you have vehicle counts, that's just the demand part. Something that I think in our industry at the moment we don't care much about is, okay, there's another piece to this equation, and it's the capacity part. Lots of assumptions made on the capacity part, but measuring demand, but lots of assumptions on the capacity side. So ATSPMs actually help to be able to quantify the performance as it is. So we're not making assumptions, we're not modeling anything. It's just purely it's the performance that's happening in the field, and that really takes the performance into account, because if you make mistakes in terms of saturation flow rate and the capacity that you're estimating for a movement, it could significantly impact the evaluation, the level of service, and the timing that's being allocated to a movement. Great question around split failures per 15 minutes, and there's a question that's asking what is the purple or heavy traffic in that split trend graph. That's a great question. Sorry, I forgot to explain that. So the heavy traffic part is, I would say it's more of a near saturated traffic condition. So it's a case where the occupancy of the stop bar detector is more than 60%, but it's less than 80%, 80% during the first 5 seconds of the red. So it means that it seems like queues were serviced, but sometimes there are remaining vehicles that haven't been serviced. So I would classify that as more of a near saturated traffic conditions. There's another question. So what are different, there's a question, so what are the different ways for interfacing, connecting SmartLink to a signal cabinet and or controller? There's different ways, so it depends on the type of controller. If it is an NTC/IP controller, it has an Ethernet port, that could be one way. We also have a software solution as well too. So if the controller, if you already have connectivity at the intersection, if you already have high-res data loggers on the controller, you just use our software. We can just enable that through our software. You don't even need the hardware. And so we also have an option for SDLC, an interface box to be able to get the data in cases where there's no Ethernet port. We integrate with a variety of controllers. So if you have any questions, you can definitely follow up with us and we can kind of go through how to make that possible. So next question is, are users able to access raw data instead of readily available tables and graph? Perfect question. Yes, so we do have APIs. So it depends on the data. I'm not going to go through the details of that, but we have APIs and you get an API key, you can access the raw data, and we're really big on being open. We don't create a closed network to not to integrate with others, but if that's of interest, we have APIs that you can access the raw data and use that. Is there a way to send notifications to engineers and techs when there is a malfunctioning piece of equipment or a significant traffic event? Again, very good question. We do have that functionality right now in our TrafficLink system. So from a maintenance perspective, if through a variety of alerts, so if there's a communications error, if there's a flash signals going to flash, or if there's a power loss, if a detector is broken, we send alerts, automated alerts, and they're configurable for sure, to whoever has been assigned to that intersection, and they'll be notified about it. They can receive a text message about it, whatever way they feel that they need the information. But in terms of significant traffic events, this is something that we haven't, that we're working kind of towards, but it's not a current functionality, but definitely a great idea to be able to automatically alert on significant traffic events. There's another question, is there any impact to the next intersection? Okay, so is there any impact to the next intersection when adjusting the timing on one intersection? For sure, there's going to be impacts, but it depends on how close that intersection is, where that intersection is. Is it dissipating through a neighborhood? Is it connected to another major intersections? For sure, that could be a major factor. So when we're looking at the data, that's why it's important for the devices to be installed along a corridor. If it's an isolated intersection, then that's not a problem. If there are close by intersections that need to be taken into account, maybe queue management needs to be done at that time, which the data can help inform as well too. Do you have any tools to help? So another question. So one of the tools is the ebook that has been shared. That could definitely help if you want more information. I have a blog post on my LinkedIn account as well too, which I walk through examples every once in a while. When I see an interesting example, I write about it and I explain what the situation was, how the data helped, and that could be another resource to be able to get more information as well too. There's lots of information on our website as well too, if that's of interest. At heavy traffic intersections, do you have a way to measure the length of the waiting queue? That's a great question. I mean, that depends on the detection, right? So the metric is very dependent on if there is some kind of sensor available to be able to measure that. For sure, that could be estimated using the turning movement count data, but again, that might be require making some assumptions, but yeah, that could be something that's possible.
Thank you, Sajad, for taking the time to answer the questions. And that brings us to the top of the hour. So I want to thank everybody for joining us today. Again, you'll be receiving a follow-up email from us with a copy of the recording of the webinar, as well as the link to download Clear Signals, our ebook. And of course, our contact information is up on the screen. So if you have any other questions or want to get in touch, please feel free to reach out to us. Thanks for joining today.